Good morning, sir. Myself, Saitija from third year Degree Department. My roll number is 23951802221. Subject Power System Analysis PSA. Subject code AEED25. AAT topic Tap Changing Transformers. Today we will discuss about tap changing transformers. Tap changing transformers. Keeping the power flowing. Discuss how this remarkable device maintains stable voltage levels in our electrical grid, ensuring reliable power deliveries to homes, businesses, worldwide, and commercial buildings. In this PPT, we will learn the tap changing transformer, keeping the power flowing. Discuss how this remarkable device maintains stable voltage levels in our electrical grid, ensuring reliable power delivered to homes, businesses, commercial, and worldwide. The problem voltage fluctuations. Electrical grid faces a constant challenges balancing supply and demand. A millions of devices switches on and off throughout the day. The electrical load on the system changes dramatically. These fluctuations are not just minor variation. They can have serious consequences for the entire power distribution network. Constant load changes. Electrical grid experiences constant changes in load as consumer turns devices on changes the load as consumer turns devices on and off throughout the day. Morning coffee makers, afternoon air conditioners, and evening lights creates shifting demand pattern that streets the system. Voltage fluctuation. This load changes causes voltage levels to fluctuate throughout the distribution network. When demand spikes, voltage can sag. When demand drops, voltage can surge. This variation can range from minor ripples to dangerous swings. Equipment damage. Fluctuation can damage sensitive electrical equipment and causes power outage. Modern electronic, industrial machineries, and medical equipment all require stable voltage to operate safely and efficiently. Without proper voltage regulation, this fluctuation could cascade throughout the grid, causing widespread equipment failing, triggering cascading blackout that could affect entire region. The solution tap changer. Tap changers are mechanical built into power transformer that solves the voltage fluctuation problems through traces. Adjustable control. They work by changing the transformer turns ratios, the relation between the number of winding in the primary and secondary coils. By adjusting the ratio, tap changers can increase or decrease the output voltage to compensate for grid fluctuations. Monitor system control decision, tap adjustment, voltage correction. Monitor system continuous monitoring of output voltage detects deviation. Monitoring system continuous monitoring of output voltage detect deviation from the desired levels. Control decision control circuit determines whether to increase or decrease the tap position. Tap adjustment mechanical or electronic system moves to new position on the winding. Voltage correction output voltage returns to the desired levels, maintaining stability. These adjustments happen automatically, often multiple times per day, ensuring end user receive constant and reliable what's happening on the grid. The beauty of tap changer lies in their simplicity. They are mechanical solution to an electrical physics principles that have been understood for over a century to solve modern power distribution challenges. Two main types, no load, on load. There are two fundamental different approaches to tap changing, each situated to different application and requirement. Understanding the distinction between the types is crucial for selecting the right solution for a given power system. No load tap changing. NLTC. How they work. NLTC requires the transformer to be completely de-energized, disconnected from the power grid before tap changes can be made. This means power must be shut off to an downstream equipment during the adjustment process. These devices are mechanically simpler, using basic switches or selectors mechanism. They are significantly less expensive than their on load counterparts and require minimal maintenance, but they can only make adjustment when the system is offline, making the unsuitable for applications requiring continuous power. Typically, are commonly found in low power distribution transformers serving residential neighborhood, small commercial facilities or industrial applications where brief power interrupts are acceptable. They are also used in situations where voltage changes are infrequent. Verify only a few timers per year when seasonal load pattern shifts. On-load tap changing. OLTC can change tap while transformer is fully energized and carrying its normal load current. This allows for voltage adjustment without any power interruption to downstream customers. Characteristics. These are highly sophisticated electromechanical systems, incorporative delivered switching, registers, and complex control circuits. They are considerably more expensive and requires regular maintenance, but they enable real-time voltage regulation. The complexity comes from needing to switch between taps without getting open circuit or short circuit. Typically, applications OLTC are essential for circuit infrastructure, power transmission, substation, major distribution hubs, hospitals, data centers, and industrial facilities whenever milliseconds of power unacceptable. They are also used in systems with highly required frequency voltage adjustments. How on-load tap changes work? Make before breakdowns. Initial connection. Current flow through the selected tap on the transformer winding. Divert bridge. A diverter switch creates a temporary bridge to an adjust tap. Parallel path. Current now flow through both taps simultaneously via the diverter. Main switch. The main switch opens, transferring all currents to the new tap. New position. Diverts opens, leaving current flowing throughout the new tap only. Seamless voltage adjustment. Transformer winding. The primary winding has multiple taps connection points, each providing a different turns ratio. These taps are physically accessible connection points along the copper or aluminum winding wires. Selector switch. A rotating or moving selector mechanism can connect to any of the above tap position, determining which portion of the winding is active in the circuit. Divert circuit. During the transition, the diverter circuit, including resistor or a reactor, bridge between taps, ensuring continuous current flow without interruption or short circuit. Control system. The electronic or electromechanical controls monitor output voltage and automatically command tap changes when voltage dip from the desired set points. Why tap changes matter? Tap changers are unsung heroes of the electrical grid, working silently and continuously to ensure electrical reaches consumer at the correct voltage. Their importance cannot be overstated. They are fundamental to modern power distribution, enable everything from lighting our home to powering data centers. Voltage regulation maintain stable voltages levels across varying loads as demand fluctuates throughout the day. Tap changes continue adjust to ensure output voltage stay within acceptable limit, typically plus or minus 5 of the nominal values. This stability is crucial for end users equipment accept consistent voltage. Grid stability prevent cascading failures and ensure reliable power delivery. When voltages drops too low, the motor draws excessive current, potential overloading circuit. When voltage is too high, insulating breakdown. Tap changer prevent these conditions, maintaining the delicate balances and keep the entire grid stable. Equipment protection and efficiency. Evolution of tap changer technology. Early 1990s, first tap changing concept developed an electrical grid expanded beyond simple point-to-point power delivery. 1970 to 1930, mechanical selector switch introduced. allowing manual tap changer after transformer de-energized. 1940 to 1950, early on-load tap changer developed using oil-filled switching mechanism to extinguish arc during transition. 1960 to 1970, solid-state electronics enabled automatic voltage regulation and remote monitoring capability. 1980 to 1990s, computerized control system integrated with SCADA network for centralized grid management. 2000, vacuum switch technologies and smart grid integration enable faster, more reliable tap changes with real-time optimization. Application where you will find them power transmission line, distribution, industrial, critical infrastructure, enable transportation system. The feature of voltage, advanced OLTC design, smart grid integration, renewable energy accommodation. Thank you, sir.